Hi, my name is Francois. I'm API Security CTO at Broadcom, and thanks for coming to this API Days New York presentation. And the topic today is post-quantum API security, preparing your APIs for Q-Day. And just a quick disclaimer here, we're not going to talk about quantum physics or the mathematics of cryptography or any of those advanced topics. But we're going to talk about what post-quantum API security is going to be about. So let's get started by looking at understanding what is the quantum threat. And if we look at where we are today in 2024, we have an extremely interconnected digital world that relies on secure communication channels and privacy of data at rest. And so things like authentication, authorization, the encryption of data, the integrity of these communications, at the foundation of all of that is this thing called public key cryptography or asymmetrical crypto. And in particular, there are two algorithms that are ubiquitous and that everybody is using. Thankfully, it makes this interconnection possible. And it makes things, all the security possible. And those two algorithms are RSA and elliptic curve. So in particular, those are really the standards upon which we secure our digital world today. If you know a little bit about crypto, you might raise your hand and say, well, what about symmetrical crypto, right? We use symmetrical crypto quite a bit and stuff like that. And that's true. But at the heart of symmetrical crypto, you still need to exchange a symmetric key. And typically that's done leveraging asymmetrical crypto. So asymmetrical crypto, public key cryptography is really at the basis of what we do. And what happens is that on Q-Day, and we'll get back to exactly when Q-Day is. Well, it won't be exact, but you'll see what I mean. When we get to this point, when a quantum computer becomes available, there's this new algorithm by Shor that basically shows you how to use something like a quantum computer. And with a few thousand qubits, with a sufficiently powerful quantum computer, you can actually really easily break RSA and elliptic curve. You can break public key cryptography the way that it's used right now. And so everything that's relying on these common standards, which is everything that's digital today, would be left open to a breach, to impersonation, to fraud, and a whole bunch of different problems. So that's what the quantum threat is. Now, don't panic. There is an actual solution. And the beauty of it is that you don't need quantum computing to protect against a quantum computer attack. There are new post-quantum crypto algorithms to replace RSA and elliptic curve. And those new algorithms are quantum resistant, even using Shor's algorithm. And the beauty of it is that these new crypto standards are compatible. You can use them with today's computers. You don't need like a fancy quantum computer for that. And these new standards are being formalized actually this year in 2024. We are closing the comment period for these new standards that are being specified by NIST in particular. So the solution is there. We just have to apply it. And that's what the problem is. So let's talk about the API-specific exposure when it comes to the post-quantum threat. So API secure connection points and access control mechanisms are numerous in terms of API security. Think of all the secure communications. For example, for us at layer 7, we tend to be in the middle of everything. We're gateway. We will have a connection with the identity layer. We will get information about API key records. We will rotate a JWK key with a token issuer. we might need to retrieve data outside of our own domain in order to enforce a policy. We might need to access or share state with other gateway deployments in the world, or we might be counting in, some API calls. There might be some microservice communication. And of course, there's the communication, the basic communication of the API client and the API itself, which is needs to be you need integrity on that communication. And in addition to just these point-to-point connections, there are access control mechanisms that rely, like everything else, on public key cryptography. So a client application calls an API and includes a token. It's a JOT specifies how this token is encoded and includes a signature. And you have some subject confirmation mechanism where you will correlate a certificate in an MTLS communication with something in a token, right? So you connect these things together for stronger authentication. You might have message level signatures or things like DPOP that allow you to confirm the subject. You might have some mediations of token where you exchange a signature for another when you're crossing security layers and things like that. So all of that stuff is affected by post-quantum, a post-quantum world, a post-quantum attack. All of these things are vulnerable. So let's look at a very specific example of a JOT-based API access control. Okay, so you've got your API in the middle here, and it has a trust relationship with an identity layer, which is responsible for issuing tokens, those JOTs, right? And this API gateway in the middle, it will pull from this identity layer the JWT key, which allows you to establish trust with that issuing authority. And on the left side, you've got an application and a user, and there's a handshake that happens, and a token gets issued to the application. And now that token is used to call the API, and it allows you to do that securely, right? So you can see what would be some of the stuff that you would find inside a JOT there. On the left side, you've got a subject. You might have some attributes like names, when the token is expired, what are the scopes. There might be some group and a whole bunch of different claims that are used at the API layer. And on the API runtime, you trust the JOT because, and its claims, everything that the JOT is including, because the signature proves the possession of a private key associated with that JWK. That's the basis of your trust, right? And the problem is that in a post-quantum world, you can just get that JWK. It's a public certificate, right? It's public, so that's easy. And using Shore and your quantum computer, you can basically deduct the private key that is held by the identity layer. And once you have the private key, you can do anything, right? You can forge any token anytime you want. You can claim any identity as part of this token. You can claim to have any permission that the identity layer would attest to. You can do that as often as you want, whenever you want. And the forged tokens that are being created on an as-needed basis, you cannot distinguish them using the JWS signature from a legitimate one, right? And so that's really what an exploit would look like in the case of JWT-based authentication for an API scenario. Okay. So what we need, like everything else, right, we're going to need post-quantum JOT tokens. And let's take a look at what that means, right? So to counter this threat, the token issuer is going to be able to switch to PQC algorithms. The token issuer will need to be able to sign these JOT tokens utilizing these new standards that are coming out. The resource server, right, like the API gateway, for example, it needs to be able to validate those signatures using those new algorithms. And so these things need to change, but the standard itself needs to change. If you look at the JOT standard, it refers to another standard called JWS, JSON Web Signature, that defines how you sign and you specify the signature and the header and stuff like that. And that itself refers to another specification, JWA, in which the valid signature algorithms today are specified. You can see them illustrated. That's a screenshot from the specification itself. On the right, you can see it's all about elliptic curve and RSA, because that's what we use everywhere today. So all these things need to change in order for us to get to that point. So at Layer 7, we just decided to try this. So we did our own PQC JWT POC. It is an imperative for Broadcom as a whole to have crypto agility. And we really need to be on the forefront of this because of how people use Layer 7 right now. So in this project, what we had to do is fork Jose for J, which is a Java library that implements those signature algorithms inside JSON Web Token. And we forked it and we added our own dilithium. So we basically went beyond what the specification says today, and we added our own dilithium signature algorithm as part of that. At the Java layer, we had to specify the use of a crypto provider. In this case, we used Bouncy Castle, which has a post-quantum crypto capable crypto provider that you can plug into your application. We rebuilt the Layer 7 gateway. We actually had to do a few other things, like allow for the creation of a key and certificate using these new algorithms as well. But in a nutshell, we did a few other things. We rebuilt our gateway. We added an endpoint for token creation because we don't have access to an identity layer that does that quite yet. And we create another endpoint for token validation using this new setup. So it works. It works great. You can paste that token that we're issuing on our side in jot.io. If you've done work with Jot, you probably are familiar with that web page. You can actually see the JWT header, which specifies the dilithium 3 algorithm. The payload is there. Of course, JWT.io says invalid signature because that they don't have the ability to support post-quantum crypto algorithms. It's not even part of the standard yet, obviously. But in the future, they would be able to validate that signature. We can actually validate a signature using our own Layer 7 gateway. And so we did a few tests to basically determine how does this dilithium signature algorithm compare to RSA 2048, which would be something commonly used today by our customers, right? Is there going to be a PQC tax to pay to switch over and retrofit this more modern crypto into your applications? And that's a really important point, because although PQC algorithms are designed to work in your current technology, you need to be prepared for any big increase in CPU usage, for example, in order to turn that switch on, right? So it actually performs not bad at all. Like, the biggest thing at this point in these initial tests that we're seeing changing is the size of the token itself, but it's still a very manageable token size for most applications. We did a comparison of the signing, our signing of the token. It's actually a little bit faster. And on the validation of that signature, the decoding of the token itself, we did see a little bit of a performance degradation, but nothing significant that indicates that there would be a significant tax to pay for switching over to PQC. So far, great news. And it's great to prove the concept on our side, make sure that we have that crypto agility and we're prepared for this. So I said I would get back to this. The big question is, when is Q Day, right? This is in some ways very similar to the Y2K situation that the generation before me had to deal with. But the big difference is Y2K, you had a very, very, very clear deadline to get ready for this. And when is Q days is everybody's guess. What does that even mean, Q day, right? Q day to me is when somebody that would be a potential attacker would have access to the capability. And so to give you an idea of when that could be, here are a couple of indicators. So on the left side, what you see is basically research results from using Shor's algorithm in order to crack a standard RSA 2048. Some of this is theoretical, but you get the idea, right? In 1994 is when Peter Shor proposed this. And in 2015, you have this research project that shows that in 26.7 hours with 1 billion qubit, you could break RSA 2048. A few years later, another project showed that you can do it in 8 hours with only 20 million qubit. At 2022, so 3 years later, 7.1 hours, but with 6.2 million qubits, right? So, and basically what you see is that the bar to break 2048 is gradually coming down as new and better ways to use Google quantum computers are being defined. So while this is going on, and by the way, this table is a screenshot of a quantum computing white paper that Broadcom recently released, so you might want to look for that. And on the right, you see where are the quantum computers, because quantum computers exist today, right? So in 2019, Google had something called Sycamore with 53 qubits. Just a few years later, IBM came up with Osprey with 433 qubits. 2023, IBM then came up with Condor with over 1,000 qubits, right? So when is a million qubit? It feels like it could be 2030 something, but nobody knows. So the timeline based on this looks like this, right? So you have on the right side Q day, that question mark target, and on the left side the deadline by which you should start your PQC retrofit project. So the first part here is the secure for period. So think about how long is a secret expected to remain private in your API, stuff that goes through your API, right? Because there's a problem known as harvest now, decrypt later. The idea is that if you can harvest data that is encrypted and in a few years down the road, you have access to a quantum computer and you can break that data that you harvested years ago. If that data still needed to remain secret for its purposes, you have a breach, right? So API traffic is really an easy target to intercept a lot of that data. So the secure for period would be stuff like that. It could also be, like the time to live of a token, although, that tends to be really, really short in comparison. And so if you add to this how long it's going to take to actually retrofit this stuff into your application, you add this together, and that's when your deadline to start your project should be. So, and you should be able to quantify both sides of this. So the time to retrofit, that left side, you have to keep in mind that some of the most critical targets for these potential future attacks tend to be large organizations. Think of, sensitive targets like a grid, an electric grid, any government-managed infrastructure system, a large corporation holding a lot of very private data, right? Could be a bank. Some of these critical targets, they tend to be really large organizations. And what we see from past experiences is that those same organizations can be slow to adapt, right? You very often see, projects to retrofit things that stretch out over more than a year, sometimes many years, right? Some environments have a very complex multi-layered architecture, and PQC retrofit is going to touch all of it. And some legacy infrastructure may lack the required crypto agility that you need to apply the PQC retrofit. So now you need to start to think about replacing some of that stuff, and that adds up to your time to retrofit. And because you can't flick the switch for all the system at once, you're going to need to have a period to overlap, between PQC support and traditional cryptography. And so this also adds to the scope and all the testing. So this time to retrofit, in some case, will take years. So if you go back to this, that left side, that could be years. Q data could be 2030. So yeah, you should probably start thinking about having a budget line item, if not in this coming budget cycle. It is just down the road. And so we encourage people to have a quantum readiness roadmap. Start thinking about this. The NIST, CISA, and NSA came up with a really helpful paper on this called Quantum Readiness Migration to Post-Quantum Crypto. You should take a look at that. You should assign a team to plan and scope the migration at some point. One of the first steps is going to be to prepare a crypto inventory of your systems. Where and how is crypto used in your organization? You're going to look at the more critical targets, and you're going to need to prioritize those. And you're going to need to discuss with technology providers. So all technology providers listening to this, right? You need to make sure that you have the crypto agility to adapt to this. And if you're a consumer of technology that relates to API and API security, you need to demand that crypto agility, because that is about to become very important. Thank you very much.